Hey, this is Professor Bennett from digitalaudiotheory.com. This programming example comes from Chapter 3, which covers sampling. Now, digital audio conversion begins with sampling, and the resulting digital signal is stored in a buffer that can be accessed or modified with two digital time operators, delays and advances. With just these tools, a simple audio delay effect can be programmed. Now, the basis of linear digital audio processing is the time shift operator. Most digital audio effects involve not only the current input, but also previous inputs or outputs. To retain these non-concurrent values, these non-simultaneous values, and to utilize them at different time points, we make use of time shift operators known as delays and advances. If we advance a signal, it arrives earlier in time, and if we delay it, it arrives later in time. The delay operator is used more commonly in audio processing since it is rare occasion that we have access to future samples, especially in real-time processing. We will utilize the delay operator to make a simple delay effect in the following programming example. In this example, you will create an effect that processes an audio file by combining it with an attenuated and delayed version of itself. There are many real-world instances of direct and delayed sounds combining. For example, this effect would be used to model a first-order reflection found in room acoustics, where the delay amount depends on the amount of extra distance traveled along the reflected path, and the gain depends on the amount of absorption happening at the reflection point. The first step is to load in an audio file and save it into a variable. We're going to use the audio read function. This audio file can be downloaded from digitalaudiotheory.com, calling it snare.wave. So we're going to save into a vector x, and the sample rate fs is going to be 44.1K. The vector x has two columns, one for each stereo channel, left and right. So we'll assign the delay amount, k, as well as the gain factor b for the delayed signal. Let's grab the length of this audio file. We'll set the delay to 0.25 seconds, although we can play with this and hear different delay amounts. Now we're going to take that and multiply it by our sample rate to figure out how many samples of delay we have. That may not exactly be an integer. A quarter of a second probably won't land exactly on a sample location, so we're going to round that to the nearest one. So we're going to have a delay of 11,025 samples. And we're going to have a gain of 0.25, which is about negative 12 dB. Okay? So the for loop will process every sample on x plus the delay, the length of the delay. We have to additionally process the delay amount so that the output doesn't become truncated. Next, we will compute the current sample, xn. All right, that's going to be down here. We're going to have xn as the current sample, and the delayed sample, xd. And those are going to be combined into an output. So look at this. Our output at our current sample n is going to be xn plus our negative 12 dB times xd, the delayed version. So let's go through this real quick. Let's start with xn. This one's going to be a little bit easier. As long as we're somewhere inside the file between the first sample and its last sample, then we're just going to grab the left and right channel out of the file and save it into xn. If we are outside the length of the input file, so if we're somewhere between capital N and capital N plus K, we're going to just pass 0 and 0. Once we've gone beyond the length of the file, it should be producing silence. So we're going to pass 0, 0, left and right. Now for the delayed version, it's a little bit trickier, but not much. If we have not yet reached the delay amount, in other words, if our sample location is less than K, then of course the delay portion is producing silence. Otherwise, we're going to grab our input at our current sample location minus the delay amount. We're going to look backwards in time. We're going to grab both channels left and right and save that into XD. Now, once we've gone outside the length of the input file, so if our current sample location minus the delay amount is greater than the length of the input file, again, we're going to pass silence. So when we run this all together, we're going to produce our Y. Now let's take a listen to it. You can hear the delay, right? Let's listen again. And we can change the delay amount. We can make it a second long, or even shorter, like 1/10 of a second. We're almost getting into the fusion region here. This is a little bit of psychoacoustics, but especially if we hit 5, whoops, let's get into like 10 milliseconds or 20 milliseconds. Whoops, there we go, 20 milliseconds. Almost sounds fused, doesn't it? It should start separating somewhere between 30 and 50. Getting there. There you go. You can clearly hear the separation. So we can also mess around with the gain. If we drop this down, we can also get a fusion of the reflected with the direct by reducing the gain. If we raise it, though, we'll more clearly hear the delayed version. Pretty neat. So you can mess with this to your heart's content. All this is available on digitalaudiotheory.com. And in the next programming example, we're going to take a look at sampling jitter. Thanks for watching.